All right, welcome back. In this video, we're going to go over resonance structures. We're also going to be doing a lot of practice problems on resonance, so you get a good idea on how to identify resonance structures, but also how to properly draw them. So if you find this video helpful, please like and subscribe. So students tend to find resonance a little bit challenging, and the reason is because either they don't know what resonance is to start off with, or they get a good idea about what resonance is, but they're executing it a little bit wrong. So my practice problems are designed to trick you. Now don't freak out, we're going to do it together, so don't worry about that. But I'm trying to trick you so you don't fall for the same traps that professors set on exams. Professors love to trick you on organic chemistry exams. So my goal is to make sure you don't fall for those tricks. Better to fall for it here in this video than on the exam. So the best thing to do is actually start off with is what is resonance? And the best thing to do for, what I see is to explain it in a story. The story I'm going to tell you, to you, it's going to sound nothing like organic chemistry. You're going to be like, why the hell is Kishan telling me the story? But I promise it has to do with resonance. So I live in San Diego currently. I have a friend, his name is Chris. He lives 2 hours away in the LA area, around that LA area. So this is a Friday night, and he comes over to get some drinks. So he drives at 2 hours to San Diego, and we're gonna spend the night to gain drunk and whatnot. So he comes over, and then we take an Uber from my place to a Sky Bar in downtown San Diego. The Sky Bar is basically like a 30-floor hotel, and on top, like the roof, is a bar. So we're both like really stressed out because we had midterms and whatever. So we were like, okay, let's start off hard, right? So we get a Long Island iced tea. It was so good that we decided to get a second one after we finished the first one. So then we look at the time, we're like, okay, the bar's closing. It's getting around like midnight. So we decide to bar hop. So we go down the elevator and we attempt to cross the street because we're like really tipsy. And we end up at a different bar. And at this bar, we have a third Long Island iced tea. Yeah, I know. So after we finish that, we're like, okay, we're pretty drunk. Let's get back to my place. And so we do that. How does this have to do anything with organic chemistry? You're probably thinking. Well, in my story, believe it or not, I mentioned resonance. I just disguised it, but I did talk about resonance. Resonance is all about electron movement. That's it. All resonance structures is a diagram showing electron movement, nothing else. This is not a mechanism. All it is electron movement. None of the atoms are changing. For example, if we started off with 2 oxygens, we're ending up with 2 oxygens. If we started off with 6 carbons, we're ending with 6 carbons. The only thing we're changing is the amount of lone pairs and the amount of double bonds or triple bonds. That is it. That's all resonance structures is. So back to my story. What changed? Well, Chris and I stayed static the entire time. We were still there from the beginning of the story to the end of the story. The type of drinks we had stayed the same. So the content, the atoms stayed the same. The only thing that changed is we bar hopped. We just went to a different bar. That's exactly what the electrons are doing. They're moving over to a more comfortable spot. Because the electrons are constantly moving. So we use diagrams, we use resonance structures to depict where the electrons are moving. The electrons are bar hopping. They're moving to different atoms. The atoms themselves don't change, it's just the electrons around those atoms is what's changing. And that is what resonance is. So we draw different resonance structures with double-headed arrows, just like this, and just like here. We draw electron movement with a head and a tail. The head of the arrow tells us where the electrons are going to. What's the destination? The tail is telling us where it's coming from. So let's look at this resonance structure. So the first thing you should know is you'll know it's a resonance structure because of the brackets. You'll see these brackets here. The brackets tell you in organic chemistry that this is a resonance structure. So we start off with this molecule here. And notice that we have an arrow here, a head and a tail. The tail is from the double bond here. And it's pointing towards this single bond. So what this is telling us is this double bond is going to break and form here, where the arrow is pointing. That's it. And this is resonance. This is showing us, this is telling us the bond is going to break and reform somewhere else. That's what resonance is. Because remember, bonds are just electrons. So I know this is a little bit complicated, so let's go over some rules for resonance first. The first rule, and the very important, is do not break any single bonds. We never ever break single bonds. The only bonds we break are double bonds and triple bonds. In addition, carbon, nitrogen, oxygen, and halogens cannot have more than 4 bonds. This means that they cannot have 4 bonds in a lone pair, and they cannot have 3 bonds in 2 lone pairs. So this sounds a little bit complicated, but I promise it's going to make a lot more sense. So here's a tip. Anytime you see a lone pair or 2 electrons like this, think of them as one bond. Even though they're not, count it as one bond. This is going to help you. So look at fluorine here. I drew up fluorine here. We have 1 pair, 2 pairs, 3 pairs, and 4 pairs of electrons. So think about this as 4 bonds. Even though they're not bonds, just think about it as bonds. It's going to help you. So I think the best thing to do is not to start out with what proper resonance structures look like, but let's talk about resonance, like improper resonance structures or illegal resonance structures. So here's a molecule here, and I drew an arrow. Why is this not a good resonance structure? Well, first thing is that I didn't draw the bars like this. I didn't draw brackets. But let's just ignore that. But why is the arrow wrong? So what I'm saying here is this 2 lone pairs here are going to transform into another bond and form a double bond here. So think about lone pairs and bonds as a currency. What lone pairs can do is they can exchange themselves. Like think about like a currency exchange. And what they can do is they can turn into a bond. And they can turn into a double bond here, basically form one bond here and form this into a double bond. But why is this bad? Why is this wrong? Well, when you do this, we form a double bond. But notice that carbon has 5 bonds. This is illegal. Carbon cannot have 5 bonds. Technically, carbon can, but just for organic chemistry A and resonance sake, carbon can only have 4 bonds. It has 1, 2, 3, 4 original, and then the 5th we just made from the lone pair, right? We made this, did this, and we created this. So this is illegal. It breaks the rule. What about this one? So same deal here. The electrons become a double bond here. But why is this illegal? This is illegal because we have technically 4 bonds in a lone pair. But remember how I said just treat the lone pair as a bond. So we have 1, 2, 3, 4, 5 bonds. Nitrogen cannot have 5 bonds. This is illegal. So this is not a good resonance structure. What about this one? This oxygen, the lone pair from the oxygen, goes over here and makes a double bond. Why is this not allowed? The reason is because oxygen here, so this oxygen has 1, 2, 3, 4, 5 bonds, in quotes. Technically 3 bonds and 2 lone pairs. But remember, think about the lone pairs as bonds. It's going to make your life much easier. Oxygen cannot have 5 bonds, so this is illegal. Do you see the pattern here? So let's do some practice problems. Are the proposed resonance structures legal or chemically acceptable? Let's do the first one here. I'm saying that the double bond here is going to break and reform here and make a double bond here. So here's a little tip. Whenever you see the arrow point to a bond, a single bond or double bond, we're forming another bond. So here, the arrow is pointing to a bond, which is this. We form another bond. We form an extra bond. That's a little tip. If the arrow points to a molecule, so say if this arrow pointed here, we add lone pairs. So anytime it points to an atom, we add lone pairs. If it points to a bond, we're adding another bond. So a single becomes a double, and a double becomes a triple. In addition, if the arrow points to an intersection, so for example, if this bond pointed here to this intersection, we add 2 lone pairs. We break the bond, so we break this bond, and we add 2 lone pairs. So is this proposed structure legal? What do you think? This is not. No. The reason is because nitrogen has 5 bonds. If we do this, 1, 2, 3, 4, and the 5th one we just added, 5. This is not allowed. So no, this is not a good structure. What about this one? So remember, like I just said, the bond is starting, so the arrow, the tail of the arrow comes from a bond. And we point it to an atom. We're pointing to the oxygen. So this means we're going to add lone pairs. We break the double bond and we add lone pairs. So is this allowed? Yes, it is. So we add 2 lone pairs. Now, here's a second pattern we're going to talk about. Anytime you see an oxygen, here's a little pro tip. Anytime you see a double bonded oxygen, think to yourself resonance. Always think of this structure here that we're going to create from this, to this. Always think this. Or vice versa, we can go like this. Draw an arrow like this and form a double bond. We get this. Very common resonance. So anytime you see this, automatically think resonance. What about this one? And I tell you to be careful. You think this is legal or illegal? You're probably thinking to yourself, this is okay. Because all we're doing is taking this bond out and putting it here. But this is not allowed. Why? Well, the carbon here, you're probably thinking, so the carbon here, it has 1 bond, 2 bonds, 3 bonds, 4 bonds. So that's fine. But it isn't. Because, remember, in the original molecule, our carbon is here. So we do have 1, 2, 3. But what about the 4th bond? Because remember, carbon must always have 4 bonds. There's a hidden hydrogen here, remember. So in the beginning of my story, I told you that we're never changing, we're never adding or losing the amount of atoms. So there is still a hydrogen here. We didn't take it away. This is resonance. It's not a mechanism. So in resonance structures, we never change the amount of atoms. The hydrogen is still there. So since the hydrogen is still there, we have 1, 2, 3, 4, 5 bonds. This is illegal. Carbon, which is in the center, cannot have more than 4 bonds. What about this one? This one. So we're breaking this double bond and we're adding it here. Is this allowed? The answer is no. Because oxygen is holding too much. It has 1, 2, 3, 4, because remember the lone pairs are, think about them as bonds. 5. Oxygen cannot have 5 bonds, so not allowed. What about this one? We're moving the double bond down here and making it here. This is not allowed either. Reason is because you have to count the number of hidden hydrogens. Remember, we're never changing the amount of hydrogens. Oh, sorry. I made a mistake. See, always check your work. Hydrogen here, 1, 2. Okay. If we move the double bond down here, remember, the same amount of atoms change, stayed the same. Well, carbon is right here, right? We have a carbon here. We have 1 bond, 2 bond, 3 bonds, and the 2 hydrogens. 1 here and 1 here. That's 5. Carbon has too much. Not allowed. Now, what about this one? This is a little bit different. This is allowed. Remember, I said that since we start from a bond and we're pointing to an atom, we're going to add lone pairs. So we destroy the triple bond and, we end up with a double bond. And that triple bond that was here, this bond here, ends up as lone pairs, as shown as the structure here. Nitrogen's fine. It has this nitrogen here is fine. 1, 2, so we have 1, 2, 3, 4 bonds. Nitrogen's happy. So we're all good. What about this one? Be careful with this one. Is this a legal structure? Is this chemically acceptable? This looks fine, right? But it isn't. It's not fine. You're probably thinking, wait a second, why not? This looks fine. Nitrogen has 4 bonds. 1, 2, 3, 4. We're all good, right? No, we're not. And this is how your professors try to trick you. Nitrogen may be all right here, but the carbons are not. Rather, the carbon is not. Let's go back here. Here we have invisible carbons here. I did not draw. And remember, the carbons always have hydrogens attached to them, if nothing else bonded to them. So if we form this double bond like this, carbon has too many bonds because it has those 3 hydrogens, the original bond, and then the double bond we've created. So it has 5. That's not allowed. So this is not acceptable. Let's make it harder. Structures can have multiple arrows to achieve legal residence. So let's look at here. This nitrogen, the lone pairs of the nitrogen, can go and form a double bond right here, right? And form a double bond. Well, this would make it illegal. Because then carbon, which is right here, already has a hydrogen that's hidden here. But also, now we have 1, 2, 3, 4, 5, 6. Oh, sorry. No hydrogen there. See, this is why. You gotta be careful. Sometimes I even make mistakes. There's a carbon here. It has 1 bond, 2 bonds, 3 bonds, 4 bonds. But if we add 1 here from the lone pair, carbon has 5 bonds. That's not allowed. But what we can do is draw another arrow here. So the adjacent double bond, we can point it towards the intersection. And remember what I said, if you point it to an intersection, we make it as lone pairs. So that's exactly what we do. is the arrow from the lone pairs, we make a double bond. And a double bond that was here, we point it towards the intersection and we add the lone pairs. And this makes it legal. It's completely fine. Let's look at here. We can take the electrons that are here and we can move them down right there. When we do this, carbon here has too many bonds, right? It already has 1, 2, 3, and 4. But if we make a double bond here, then it's going to have 5. So we're going to take the double bond here and point it to the intersection, and we put lone pairs. Now, how do you know where to put the arrows? You're probably thinking to yourself. So arrows must move, the electrons must move to the next available location, well, the next nearest location. What do I mean by this? So I cannot draw this arrow like this, or something like that. Electrons cannot migrate that far. They can only migrate to the next bond over, like this, the nearest bond. So this is exactly what's happening. The double bond goes to the nearest location, the nearest intersection it can. It doesn't do a whole 180 or 360 or anything like that. It has to go to the nearest location it can, the nearest bond or nearest intersection. That's why people mess up resonance. There were like, okay, someone would be like, why can't we just do this? Right? Why is this not allowed? Electrons cannot move that far. They physically cannot move that far. They can only move, think about, I don't know, like Monopoly, for example. I don't know. Monopoly, you only roll a 1. You can only roll a 1. Imagine that. So you can only move one space. Or, oh, you know what? Even better, chess. Everything are pawns, okay? Pawns can only move one space. Think about it like that. Electrons can only move one space. Electrons can only move one space. We're not moving two spaces, right? We cannot do this. That's two spaces. So think about it like that. So now let's draw the chemically accepted resonance structures for this. Okay. So you're probably thinking to yourself, why don't we just do this and move the bond here, right? But what do we do with these lone pairs? We can't just leave them. We can't do this, right? Because this is like moving two spaces. That's not allowed. So what the hell do we do? Well, we move one space. We move the double bond to the end here, and we form lone pairs, because that's an intersection. Pretend that's an intersection. We make the lone pairs into a double bond here. And that would be the correct resonance structure. Ta-da! Like that. So what about this one? I accidentally gave the answer a little bit there, but remember the pattern I told you about with the double bond and the oxygens? So you should immediately think, oh, we have a double bond oxygen. We can move the arrow like this and hit the, aim it at the oxygen. Aim the arrowhead at the oxygen. So we create a lone pair like that. But when we do this, you're probably like, wait, isn't that it? Well, no, because there's a carbon here. The carbon must have 4 bonds. We just eliminate one of the bonds, right? We move this bond right here into a lone pair, so it's gone. So you have to take this and go like that. Take the lone pairs and make a double bond, right? One space over. And that would be acceptable resonance. Carbon is happy. Ta-da! Like that. And that's it for this video. Hopefully you found this helpful. If you guys want me to make more resonance videos, I'll be more than happy to. Just let me know. But until next time, later.